Good day. The topic of our research is CBR method for decision-making support and operation efficiency ensuring of complex technical systems. Problem statement. Currently, there is an increase in the use of decision-making technologies for the effective operation of complex technical systems, which are hierarchical structures with non-trivial internal connections, multiple functional subsystems, components, elements, and their mutual connections, which are in various states of failure. Complex technical systems are classified as a system of critical use. As the safety requirements for expensive complex technical system increase, the requirements for their efficiency also increase, depending on the ability to operate the systems in the event of partial failures, time and resource during operation. In order to identify signs of pre-failure technical condition of complex technical system equipment of critical use, at an early development stage, it's necessary to use intelligent information technologies to support decision-making. The core of such information technologies are conceptual stochastic models and methods for diagnosing vehicles, effective intelligent informational systems for assessing, forecasting, and controlling vehicles. In order to increase the operational efficiency of critical ship and complex technical systems, solving the necessary decision-making problem is complicated due to the need to take into account a significant number of various factors. First of all, this is a large amount of information required to make an appropriate decision. When assessing, predicting, and controlling a vehicle, it's necessary to take into account the mutual influence and different degrees of subsystems failure, components, elements, and their parameters on each other. So, accordance with the requirements of Register of Maritime Shipping, all ships must be equipped with systems based on artificial intelligence technology. To implement such technology, appropriate algorithm and software tools are required to provide support for decision-making that is adequate to the goal. However, analysis and assessment for the technical characteristics of complex technical system equipment and the development of control actions in most cases are often carried out by ship operators on the basis of heuristic rules, as we can see in the works of different authors. It's impossible for personnel servicing a complex technical system of critical applications to analyze and evaluate the technical condition of system equipment. This problem can be solved by using methods used in intelligent information systems. Methods for finding solutions in such systems based on precedents are an approach based on the use of analogies with previously solved problems to find and adapt solutions to new situations. Similar methods include the steps that form a CBR cycle: capturing precedents from the precedent library, indexing, search for the most suitable precedents of a new task, adaptation, and evaluation and implementation. Advantages of CBR are adaptability, working with incomplete information, learning ability. As we can see in the slides, our methods of presenting precedents can be visualized with CBR cycle structure. We can see stages formation of the task with array of ontologies and input diagnostic parameters of technical condition complex technical system, which makes it possible to create a new precedent. And after that, we can remove removal of precedent. We can make procedure of removal precedent with the nearest neighbor method. After that, we can provide modifications for adaptation with the transformational method. And after that, we need to do verification and formation of decision. Updated decision can be used for conclusion of a decision, and final precedent preservation provides the editing to knowledge base, new precedent with a database of ontologies, rule base, and the base of precedents. Um, our method can be formalized in such formula that we can see in the slide. Simple parametric representation, presentation of precedent in the form as a set of parameters with specific values and a solution, decision-making, diagnosis, and recommendations. We can see the parameters which can describe the use case, set of assessments of subsystem failure risk components, elements, and their interconnections. And we can see set of damages and set of probabilities and performance assessment of subsystems on intercomponent intersystems, set of refined specific estimates, technical condition parameters of subsystems, saved values of many updated estimates, diagnosis and recommendations, some of subsystems, intersystems, and so on. On this slide, we can see block diagram of the intelligent information system with CBR assessment, forecasting, and controlling of the complex technical system vehicle. We can see such blocks as structure of a complex technical system, model of formalization of expert evaluations, request formalization model, intelligent interface database, a model of recommendations for ensuring the effectiveness of a complex technical system, block of extraction of precedents, and precedent base, which is included in the knowledge base block. On this slide, we can see decision sequence diagram, which can be useful for understanding the software we made due to this method. We can see the main form of the interface is data processing module, precedent extraction module, adaptation module, and knowledge base. The whole 17 stages we can see in this slide, from import of input data configuration models and data transfer due to sending request per preserve precedent and sending a notification about the status of precedent which was added to knowledge base. In this slide, we can see such an experimental results with the main engine subsystem failure risk prediction calculation. We can see on this slide is a table of predictions, a priori, a posteriori, some of recommendations with expert things, and dashboard where we can see the main engine risk prediction from 1,000 till 20,000 hours of using subsystem. On this slide, we can see experiment results. Actually, the first graph is the time to determine the technical condition of a complex system. Is based on the number of precedents. We can see time from 0 till 100 milliseconds, and precedent numbers and the second X. And we can see the next graph, it's execution time of computational processes depending on the number of generated precedents. In three types, one flow, two flows, or four flows. Flow means threads. One of the threads with calculation parallel parallel calculations. Result discussion with an increase in the precedence number in the precedence library determining complex technical system technical condition time increases, but it doesn't significantly affect the overall time spent on the evaluating the technical condition of the researched ship power plant subsystems. Despite such a shortcoming, studies have shown the possibility of applying the method of reasoning based on CBR precedents and its expedient to use it for decision making in real operation conditions. The developed information intelligence system has high performance. As a conclusion, we can say that our system experimental studies for assessing and prediction the technical characteristics of complex systems showed that the time required to find the nearest precedent with 10,000 precedents in the knowledge base was about 370 milliseconds. The decision-making sequence using the proposed system with the CBR cycle, taking into account the operations for processing and structuring data according to precedents within the framework of the functioning of the development application software system, has high performance, ensures work with incomplete information, versatility and learning ability when supporting decision making. According to the distributed computing mode, it becomes possible to reduce time costs by up to 28% when using two data streams isolated from each other, and up to 42% when the computing load is divided into 4 separate data streams. So, thanks for attention.